Welcome guys. Today we will discuss about Kruskal'S algorithm. Kruskal'S algorithm is a minimum spanning tree algorithm that takes a graph as input and finds the subset of the edges of that graph which form a tree that includes every vertex that has the minimum sum of weight among all the trees that can be formed from the graph. How does a Kruskal'S algorithm work? Sort all the edges from the low weight to the high weight and take the edge with the lowest weight and add it to the spanning tree. If adding the edge created a cycle, then reject this edge. Keep adding the edges until we reach all the vertices. Here's an example which will explain about Kruskal'S algorithm. Let us consider a graph with 4 vertices A, B, C, D. Keeping A as the position, reaching B with a weight 2, reaching C with a weight 3 and reaching D with a weight 1. Keeping B as the position, reaching C with a weight 1 and reaching D with a weight 2. Next we move to the next position C, keeping C and moving to D with a weight of 2. We came to know that A, D is found to be the lowest weight, so we need to draw a line from A to D. Then B, C is the next lowest element, so we need to draw a line from B to C. Next we came to know that A, B with a weight of 2 is the lowest weight, so we need to draw a line from A to D. The next lowest weight is the B, D, but B, D cannot be drawn because it forms a cycle, so it is rejected.
In graph, we are going to see Prim's algorithm for a minimum spanning tree. Before we going to see that, let's understand what is the minimum spanning tree. If we given a graph, a minimum spanning tree is a subgraph such that all the vertices in the original graph exist in a subgraph and the subgraph is connected and there are no cycles in the subgraph. So essentially we are going to construct a tree out of the vertices and edges in the graph such that we cover all the vertices. So Prim's algorithm, it is a greedy algorithm that finds a minimum spanning tree for a weighted undirected graph and is mainly used for a dense graph. Some of the applications are finding airline routes, clustering and routing algorithms, etc. So why do we call Prim's algorithm as a minimum spanning tree? Because the edges we want the summation of the widths of those edges to be minimum. So with this in mind, let's take a look at an example. In this graph, we are going to construct a MST tree. That is, MST means minimum spanning tree. In this graph, there are 6 vertices A, B, C, D, E and F. Step 1 in Prim's algorithm is to choose the arbitrary start vertex. If say I am going to start at A, when we visit A, we need to assign 1 to A. We came to know that the shortest path have been obtained to reach B from A and C from A and F from A is 3 to 1. For the next tabular column, we need to start with shortest distance which entered in previous tabular column, that is F. When we visit F, we need to assign F to 1. We came to know that the shortest distance have been obtained to reach D from F is 2 and E from F is 1. For the next tabular column, we need to start with the shortest distance which is entered in previous tabular column, that is E. When we visit E, we need to assign E to 1. Then we came to know that we don't replace the value for E because it's already have the shortest distance to reach from C to E and E to F. So for the next tabular column, we need to start with the shortest distance which is entered in previous tabular column, that is C. When we visit C, we need to assign C to 1. Then we came to know that we don't replace the value for C because it's already have the shortest distance to reach C and E. So next, for the tabular column, we need to start with the shortest distance which is entered in the previous step, that is D. When we visit D, we need to assign D to 1. Then we came to know that the shortest distance have been obtained to reach D from D is 2 and to C and F, they already having a shortest distance. So for the next tabular column, we need to start with the shortest distance which is entered in the previous step, that is B. When we visit B, we need to assign B to 1. We came to know that we don't replace value for B because it's already have the shortest distance to reach from D to B. Then we need to draw a graph based on the last tabular column, and this is the final and equivalent graph. And then we need to calculate the cost of the tree using the connected graph.
Okay, now we look into Dijkstra'S algorithm. What is Dijkstra'S algorithm? With Dijkstra'S algorithm, you can find the shortest path between nodes in a graph. Particularly, you can find the shortest path from a node that you choose, called the source node, to all other nodes in the graph, producing a shortest path tree. As for its application, this algorithm is used in GPS devices to find the shortest path between the current location and the destination. It also has broad applications in industry, especially in domains that require modeling networks. Before looking into requirements, we will know a bit about directed graphs and weighted graphs. What is a directed graph? If for every pair of connected nodes, you can only go from one node to another in a specific or a particular direction. We use arrows instead of simple lines to present these directed edges. What is a weighted graph? A weighted graph is a graph whose edges have a weight or a cost. The weight of an edge can represent a distance, time, or anything that models connection between the pair of the nodes it connects. For example, in the weighted graph below, you can see a number next to each edge. This number is used to represent the weight of the corresponding edge. So this is an example of a directed and a weighted graph. Requirements for Dijkstra's algorithm. Dijkstra's algorithm can only work with graphs that are directed and have positive weights. This is because during the process, the weights of the edges have to be added to find the shortest path. If there is a negative weight in the graph, then the algorithm will not work properly. Once a node has been marked as visited, the current path to that node is marked as the shortest path.
Now see an example for Dijkstra's algorithm. In this graph, A is the source node, so weight of A is 0 and it remains unchanged. With A as source node, we are going to find the shortest path by adding the weights of the edges. The other vertices have weight as infinity and the beginning and will be changed when they are visited. As A is the source node, we visit A first. From A, we have two edges, that is one to B and the another one to D. The edge weight of AB is 2 and the edge weight of AD is 1. So with respect to the edge weight, the weight of B changes to 2 and the weight of D changes to 1. As we don't have any other edges to any other vertices, the weight of other vertices remains as infinity. We compare the weight of B and D. Here D has the smaller weight, so we visit D as the next node. From D we have edges to C, F, G and E. As we already know that the weight of D is 1, we add 1 with each and every edge weight to calculate the weight of each vertices. From D the weight of C is weight of the edge DC plus weight of D. That is 1 plus 2, which is 3. The weight of C now becomes 3. Same as for E. As the edge weight of DE is 2 and the weight of D is 1, it becomes 1 plus 2, 3. E also has the same weight as C. For F, DEF plus edge weight of DEF plus C, D. Therefore, 1 plus 8 becomes 9 and the weight of F becomes 9. From D to G, the edge weight is 4 and we already know that D's weight is 1. When we sum it, 1 plus 4 becomes 5 and the edge weight and the weight of G becomes 5. We compare the weights of the vertices B, C, E, F and G. B has smaller weight, so we visit B as the next node. From B we have two edges, one is to D and another one is to E. As B is already visited, the weight of B remains unchanged. We calculate the weight of E with respect to the B, which is the edge weight of BE plus the weight of B. As we know that the weight of B is 2 and the weight of edge BE is 10, when we add we get 12. As we have already calculated the weight of E with respect to D, we compare the weight of E with respect to D and E, where 12 is greater than 3. So the weight of E remains unchanged. Now we compare the weights of C, E, F and G. C and E have similar weight or same weight. So we follow the alphabetical order and we visit C as the next node. From C we have edges to A and F. As A is the source node, the weight of A remains unchanged. And with the edge weight of CF is 5. And we already know that the weight of C is 3. So when we add it, 3 plus 5 becomes 8. The weight of F with respect to C is 8 and weight of F with respect to D is 9. When we compare it, 8 is less than 9. 8 is less than 9. So we replace the weight of F by 8. Now we visit E as the next node. From E we have edge to G. As we know that the weight of E is 3 and the edge weight of EG is 6, the weight of G with respect to E becomes 9. 9 is greater than 5. So the weight of G remains unchanged. As 9 is greater than 5, the weight of G remains unchanged. Now we compare the weight of F and G. Here G has the smaller weight, so we visit G as the next node. From G we have one edge to F. As we know that the weight of G is 5 and the edge weight of G and GF is 1, we add it. 5 plus 1 becomes 6. The weight of F with respect to G becomes 6 and we compare it with the existing F's weight. 6 is less than 8. So we replace F weight with 6. Now we visit the F node. Here no change happens and each and every node no change happens. And we have found the weight of each and every node. The shortest path from the source is A to A and A to B equal to 2, A to C is equal to 3, A to D equal to 1, A to E equal to 3 and A to F is equal to 6 and at last A to G is equal to 5. Thank you friends for listening to our video. Please like and share.